Good morning, ma'am. Myself, Mahizabin from Computer Science and Engineering. Today, my presentation topic is backtracking, the general method explained, and the subject advanced data structure and algorithm analysis. And the subject code is 23 CSE 301. Now let us know what is backtracking. Backtracking is a problem-solving technique that incrementally builds candidate solution part by part. And backtracking strategy retreat is it systematically treats options step by step and efficiently uploads when a dead end is reached. And coming to the common applications of backtracking, the method is commonly used for solving puzzles, satisfying complex constraints, and combinational problems. The core idea: explore and undo. Explore choices. At each stage of the problem, explore all available possible choices or extension to the current partial solution. Constraints check. Immediately check if the newly added choice volatiles any problem constraints. Undo and retry. If a choice leads to failure or an invalid stage, it is undone, backtracked, and the algorithm tries the next available choice. Formalizing the problem structure. A solution is typically represented as a tuple of decision, where each decision must adhere to specific limits. Tuple representation. Solution are expressed as an n tuple x1, x2, and so on xn, where each element xi is chosen from a finite set that is S. The goal is to find the tuple that satisfies a given set of explicit and implicit constraints. For example, the 8 queen problem. The task is to place right chess queens on 8 by 8 chessboard, such as two queens threaten each other. No two queens can share the same row, column, or diagonal. Now let us see explicit and implicit constraints. Backtracking power lies in how it handles these two type of constraints to limit the space, they limit the search space. Coming to the explicit constraints, it defines the basic domain of each element. Rule Rules restricting each element possible values. For example, x size belongs to S, often defines the shape of the solution space. Coming to the implicit constraints, it defines a required relationships between elements. Rules relating elements to each other. For example, in 8 queen problem, no two queens can share a diagonal. These are checked dynamically at every step. Backtracking checks constraints at every step to pure invalid partial solution before they become full solutions. Backtracking as depth first search. The process of solving a problem, wise backtracking can be visualized as traversing a tree. Here we can see the diagram. This diagram shows partial solution, dead end and front end, and the start at root. Here is the essential terminology to know. Live node, a node that has been generated, but its children have not yet been fully explored. Coming to the E node, expanding node. The node currently being processed and expanded, the one whose children are being generated and checked against constraints. Dead node, a node that cannot lead to a complete solution either because it has no valid children or all its parts lead to the dead end. Solution state, a node that represents a complete and valid tuple satisfying all both explicit and implicit constraints. Here is the general backtracking algorithm outline. Here are the 5 stages of backtracking algorithm outline. A systematic recursive approach to traversing the solution space path, space tree. Start empty, try extensive, invalid points, found solution, and lastly, recursive and repeat. Here we can see when and why. Why we use backtracking? Backtracking shines in problems where constraints are difficulty to satisfy simultaneously and brute forcing in infeasible. Coming to the ideal scenarios, problems with multiple solutions or complex interdependent constraints. Any such problems that can be formulated as a sequence of choice leading to a goal. When the solution space is large, but purifying can significantly reduce the efficient set size. Coming to the classic backtracking problem, Sudoku, filling in a grid that numbers constraints. NQS, a generalized chessboard placement problem. Hamiltonian path, finding a path that visits every vertex actually once. Here, here the important note is while effective backtracking can still be exponential time complexity in a worst case, but it offers the most feasible approach for these type of combinational problems. Here is the summary of backtracking in action. A systematic approach. Backtracking is a systematic method of exploring the solution space of constraint satisfaction problems, ensuring no valid path is missed. Efficiency through pruning. It primarily efficient gains comes back from its availability to check constraints early and discard partial candidates that cannot possibly lead to a solution. Thank you.